Well, hi, good morning. Thanks so much for joining me again in my shop. Day 2 with my signal tracer here. Yesterday I was just kind of generally exploring it, and I'm left with the impression that this is not working well at all. That's the final impression. The part that really did it for me was hooking up my whiz-bang loop antenna and hearing really no radio stations coming out of it. I know I've done this in the past, and this thing has produced radio stations off of long wire antennas and that, but it doesn't seem to do anything anymore. I was so concerned, I tested my antenna on another radio later in the day. There's nothing wrong with the antenna, it's working just fine. So, all fingers are pointing at this thing as being a problem. I thank you very much for the comments on the first video there. I've read through them all and replied to a couple, and one of them suggesting, one of the comments was suggesting that leaky capacitors in the power supply could result in an elevated chassis voltage and therefore give me the tingle shock or light my little neon bulb and that. So we're going to explore that question. In fact, we're going to just stick with the power supply to start off with this guy. He hasn't been on yet today, so there's no charge in it unless the charge is held on since yesterday, which is really extremely unlikely. So we can fiddle around with an ohm meter and stuff like that. And we're all set to do the very first test that's mentioned in the manual after this is built. This was a kit, right? The first test is to look at the resistance of the power supply. You literally look across the second filter capacitor, and you're basically looking into the radio, or into the signal tracer and back into the power supply. And the expectation is the resistance is over 300,000 ohms. So we're all set to do the test. I already have my meter connected, so we're going to do it. So 300,000 ohms, here we go. How come it's reading negative? Well, that's suggesting that there's still some voltage left in here. Let's look for that. Going up. It's going up. How in the heck does it go up? Yeah. So this isn't even plugged into the wall. It's just a hunk of metal sitting here, although I don't even have a scope lead connected. This is a hunk of metal sitting on my bench. My God, I found free energy. It's been hidden inside this signal tracer all this time. I'm trying to think. Did I short something out and knock out a voltage which is now coming back? I didn't really do much here before I turned the camera on. Son of a gun. Now the next question is this voltage throwing off my my test reading here? I'm going to use the device's own ground lead to ground out this voltage here. Okay, I'm going to give it a little bit of time. So a source of voltage in a receiver or a device like this, when it's completely discharged, you expect it to be discharged, especially a rising voltage, suggests to me that once again I'm encountering this battery effect from bad capacitors that have moisture in them, and it creates a bit of a galvanic action between the different types of metals that are inside the capacitor. Aluminum being the powerful, it's high on the electromotive series. So if there's any aluminum in those capacitors, then it'd be easy to generate a voltage back of some measurable amount. Okay, let's take the short off, and we'll see if this voltage starts from zero and starts going up again. So this low voltage would not disturb a resistance reading, I don't think. So I'm going to put the short on again. flip over to resistance. 300,000 or above is the magic number. So I believe I should be able to release this. We certainly shouldn't see a negative sign here at that point. And we should get a resistance reading that's reliable and until that voltage builds up. There we go. Let's see. I have no idea what I'm doing. What am I doing? Here we go. What's the action on this meter? What am I nuts? Maybe there's a lead. Am I nuts here? I can't be nuts. Yes, I could be nuts. I got these in correctly. Sometimes I'm using different meters. I accidentally put the leads into the wrong spot. Well, you know, I could just be measuring a resistance. It's just taking a long time to charge up capacitors. That's probably all this is. It's not negative anymore. Enough time has gone by, though, to charge may be coming back. So we're getting up in the 300,000 range. Anybody want to believe this? Can we possibly believe this reading? That's why I brought his brother along. Actually, this is a distant cousin. Really leaves you wondering, doesn't it? So this meter is saying 5 megohms. The more I do this cross-checking between instruments and that, the more unsettled I become about everything. And if you change scales, I bet you we get a totally different reading. This is a 200 scale. I think it's going to eventually go over. 20 megohms, we get 15 megohms. I don't know what to make of this. So I'm going to argue this initial test, because of internal voltages, perhaps, or for reasons I don't understand, the test is unreliable. It had the unit on it, so we know it works. So this test is actually a proof test. You want to do just before the first time you turn something like this on. All the capacitors would be fresh and new. They certainly wouldn't have any of this galvanic voltage in them. And you can get away with that test. But I couldn't. So the next best test, I put them right back on. I'm going to turn the unit on and we're going to measure the B plus voltage on here. So we're going to do it right across the. You know what? I'm going to do this a little differently. I'm going to clip onto the ground here, some appropriate place, onto the chassis. Why would I pick that spot? Let's pick this spot. Okay, I'm going to put in one regular probe here. We're going to probe around a little bit. Okay, let's check, see how we're doing here. Good. Put this up on DC voltage, 1000 scale, because I think we're looking at 200 or 300 volts here anyway. So I think we're all set to turn them on. Let's volume down, leave it on radio. Okay, plug them in. If I sound like I'm talking to myself more than you, I am. I am talking to myself. Hey, I mentioned we have a visitor cat. Hey, things are going great with this cat. This is a really, really friendly, interactive cat. And all three of the cats are very close to just full bore playing together. They're just right on the edge of it. So I bet you today I'll see all three of the cats in this house starting to play together. Okay, that's an exciting thing for me. Let me just clip this back so it doesn't go somewhere undesirable. So the objective here is to make a DC measurement on the two filter capacitor positive terminals. I'm just practicing. One is here, one is here, and then we'll switch this to AC, and we'll make an AC measurement. And then I have the scope I want to put this on too. And what we're looking for is how well filtered is this. That's our first step. Okay, wait, I'm not going to turn anything on by looking at my computer. Okay, we're ready? Yeah, I don't think it's switched on yet. Oh yes, it is on. Oh no, it isn't. Here we go. Okay. Whereas in my case, with dim lights, I could take a device, unknown about its condition, plug it in using the dim lights, turn it on, those lights come on full, and then I know there's a problem in the device. They wouldn't have to do this resistance test. The dim lights are, the dim light technique or whatever, I like it. It's really great. Maybe it's because dim rhymes with Jim. Okay, full power. And this guy has to be ready to go. On the meter there. This is, I believe this is the second capacitor. So this is the highly filtered one. 266, and now this will be the first capacitor, less filtered. 275, that all makes sense. And we're going to switch this to AC. Now I'm what are you doing there? What are you reading? So I think the reason that you're getting a reading on a meter with the lead sitting out here in space is it's really coming from the chassis over here. I have no grounded instruments attached to this at all. It's plugged into an isolation transformer, therefore its voltage relative to Earth is a little questionable. And I'm sure there is a capacitive connection through transformers and whatnot back to the power system to some degree, so I can make this measurement. Otherwise, if there was absolutely nothing, I would have to think this would have to be zero. So having thought all that through, probably wrong about everything, we'll now look for AC voltage on the second filter cap. So that looks pretty high to me. Whoa, we're getting all kinds of readings here. Let's get this better. So it just bled it all away. My list of things I cannot explain just keeps getting longer and longer. Oh, son of a gun, I can explain that. I can explain that. Why would taking a reading at the top of the capacitor, and I'm going to make sure I don't slip this time, cause the AC voltage to bleed down? I would almost suggest that there's absolutely no load on this power supply. Ooh, I almost slipped again. Oh, I see how it slipped too. Slipped right through the hole in the terminal. Down to the chassis. So we try the first capacitor. The same effect. Okay, never seen that before. What does it mean? I don't know. Now I don't take, like this is taking an AC reading in the presence of a large DC voltage. I'm sure some meters can hack it. Certainly the old style indicating meters, the non-electronic ones, no, you couldn't do this. You couldn't test AC with DC sitting there. Even if you put your meter on the AC scale, the DC will still affect it. But these ones, I've seen it done with this kind of meter. I got another one of these. Let's try the other one. You know, I've become much less concerned about the fact that I don't understand stuff as I get older. Because in the last couple of months, I've learned that some of the most fundamental things in this world are not understood, even by the greatest experts. Things like gravity. It's not understood. And the other day I watched a video on momentum. Momentum is not understood. Momentum. Oh my God. So if I don't understand something about this, I feel fine. So we want to put this onto voltage here before I... First we'll do the DC voltage. The slow motion meter. Here we go. Okay, so it's beeping because it's over 40 volts. So 263, and on the first one, 270. So it's the same reading as the other meter, of course. Now, we're going to flip this to AC. Goodness knows what will happen now. Second filter capacitor. Don't slide through the hole this time. This meter's not at all happy about this. That meter was not a happy camper on that test. Okay, let's go with the tried and true method. We'll look at it on the oscilloscope and we can actually measure off the amount of ripple that's in the signal. So you can see the scope in the background here. First we'll make a nice, we'll get this off here. Remember, Jim, this is on. Don't forget that. Just not stable. Okay, that's going to stay there. Setting the scope up. So we're expecting a large voltage on here. So we'll set the scope for 50 volts here. We're running on channel 2. Channel 2 is on. How come I don't see anything from channel 2 yet? Okay, I'm going to put the trigger onto line. Hopefully we can get a... Where is it? Where'd you go, man? Beam finder. Here's the beam finder. I guess it's not triggering yet. Let me just... Hey, man. What's up with this? What's up with this guy? We should see something. Oh, he's going so fast. That's what it is. He's just going too fast. They're roaring along here at 1,000,000 miles an hour. There. There we go. So here's an anomaly. No, I won't bother. I was going to give you a physics anomaly, but let's just stay focused on what we're doing here. Yeah, it's very unsettling to watch these videos on physics when you think all the answers are coming, and after you've watched enough of them, you realize what physics people are dealing with aren't answers. They're dealing with questions. And some of the things that you might think had been settled because we were taught them, like the double slit experiment. I was taught that in high school in the 70s, for crying out loud. The dual nature of matter. You know, the double slit experiment is still confusing to physicists, even now. See how excited I get about this stuff? Okay, focus, man, focus. Hocus pocus. We will now clip on. Oh, not like that. Well, it wouldn't really matter. It's not going to hurt a scope to have it not set right. Okay, so we're going on to, this is the first capacitor now. I'm just checking my fingers before I stick them in there, or you're watching me. Here we go. Now. Okay, hooked on beautifully. So it's just a movement to here. Is that all that just happened? Oh, it didn't move anywhere. Oh, because I've got this on AC. It's okay, I'll catch up with myself in a moment here. So let's put the 0. Let's put the 0 right on the bottom line here. Put DC 100, 200, 265. So it's giving the same voltage reading here as the now. I don't see any ripple at this point. I can see no ripple in this much signal. I see no ripple at all. So I can switch this to AC. I'm going to move it up in the middle so we can see it better. And we're going to go looking for the ripple. Okay, so I've got this going too fast still. That's part of the reason we couldn't see the ripple. Back up. Okay, now we can see the ripple even at 50. Let me turn down the brightness here before I burn your computer screen out. There be the ripple. Okay, checking the 0 again. Right. So we can measure it now using the AC setting here. Advance this till it takes up roughly 1 division, peak to peak. Pick that. So that's roughly 1 division peak to peak. So we're looking at 5 volts of ripple. So 5 volts of variation on top of 300 volts. So that's roughly a 1% ripple. And it doesn't actually sound that bad to me. Now, without changing any of the settings on the scope, I'm going to move the lead to the other capacitor and we should see almost no ripple. This is the magic of 2 capacitors. Magic of it. And we're seeing almost no ripple. So now if I advance this till we see the funny shape to it. Kind of bopping up and down a little bit too, so won't worry about that part. That's roughly a division. Now it's 0.2. So we're looking at 1/5 of a volt in 300, which would be 1 volt in 1500, which would be something like a tiny part of 1% ripple. So it's suggesting to me that there isn't a problem with the power supply here. I haven't done anything here that would make me think there's a problem here. My own experience with these metal-clad capacitors has been really, really good. So I have to resolve whether there's a concern here. So what we'll do is we'll leave these as they are. I think we can assume there isn't a problem with the power supply of any significance. We'll move forward with more testing. If a hum shows up at some point, and I can already tell you it's probably not going to happen, then we can always revert back to the power supply and fiddle around with extra capacitance and stuff like that and see if that hum is really power supply related. Now there's a message right in the manual that says a couple things. One, in audio mode you're going to hear a hum no matter what you do when you turn the levels up. There is a hum that just comes along with this guy. I don't think you should hear a hum in RF mode. It also warns that if you turn the audio up high enough, and this was kind of funny, if you turn the audio up high enough, you will get a feedback. But the feedback is actually from the speaker vibrating the cabinet, vibrating the components. So that's how that feedback works. And the reason for that is because the gain is extremely high. That's what it says in the manual. So where are we at now? I'm going to go on to the next step, which would be, I think there's a nice table of tube voltages And we'll go through and check all the tube voltages according to the table in the manual. First, I'm going to disconnect this before I get into trouble. So a little bit of hum on the first capacitor, which is the takeoff for the output tube that drives the speaker. That little bit of hum is considered to be so low as to be immaterial coming out of the speaker. Even if you could hear that hum, it's really coming from the power supply. Even if you can hear that hum, when you start using the instrument and you have what's called program material coming out of it, things you're testing, it will overwhelm the hum so much the hum will not matter. So it says in the manual. So we're not to get too caught up in a few unimportant hums. So the voltage table on the manual, let's go take a look at that. So, well, let's stop here and look at the schematic for a minute and take a look at these two capacitors. These are the two that we've been testing. I've been testing just now as best I can. I'm not really testing the capacitors, but just looking at the voltage here and here on the scope and seeing there's pretty easily visible ripple here and really nothing much here at all, just as you would expect, exactly as you would expect. See the B plus takeoff off of this first capacitor is what goes right to the output tube. Very typical in most radios. How it's done, because you can draw a bit of power here without pulling it through this resistor. You can also leave this alone then, so this resistor provides some isolation from the varying current draw from the speaker here as it operates, so you don't start flexing the voltage here too much. Like if you move this wire over here, you start flexing this voltage up and down, and this voltage is going to, tube plates and tube shields, screens and stuff like that, and it's going to be a problem. So this is how most radios are built. They don't waste the highly filtered stuff on the speaker. It's not needed. They use the highly filtered stuff earlier in the set because any hum there is going to be amplified coming through. Okay, enough of that. So how did I get a shock from this? Now, number one, maybe I'm mistaken in how I got a shock. But I don't think I am. The shock came between when my hand was between my capacitor checker and this guy. Both of them have this kind of power supply. There's no connection between the power line coming in and the rest of the stuff in here. So exactly how I got a shock by grounding myself to the chassis of another machine. I think it all comes down to the capacitance inside these power transformers. So there was a suggestion that if these capacitors were bad and they were leaky enough that you could draw a resistor here if you wanted, that this current flow then through the resistor of the capacitor, the leakage of the capacitor, would raise the potential of the chassis. But my question would be, raise it against what? What is it getting raised against? I don't think it can raise it any more than sticking resistors here would raise this, unless there's a resistance between here and here, which there isn't supposed to be. It's supposed to be the same. So I'm not sure a leak in these capacitors can generate, in this case, can generate a case voltage that's going to give you a shock. Am I right about that? I don't know. That's what I'm thinking. Now let's go look at this table now. This great manual. Look at lots of words in this manual. Here's the table we need. Okay, there we are. It just shows each tube and what voltages you should measure. So I'm just going to go through this process of checking all these voltages. I'm going to do it all off camera. I'll do it quickly that way. If I do it on camera, it will take me much, much longer. I'll do it quickly, and if anything's out of the norm, you will hear about it. Well, it didn't take very long before I turned on the video. So I'm on the tube number 2, vacuum tube number 2, pin number 5. If you look at the chart there, vacuum tube number 2, 6 GM6, pin number 5, you should see 190 volts. Okay, so you're looking at this meter here. Pin number 5, let me count them carefully again. 1, 2, 3, 4, 5, same. It's definitely V2, no doubt about it. So here's the actual reading. 260 instead of 190. And that's in the RF position. In the AF position, it should be 150. $260. You know, the difference between 150 and 260, that's a lot. Well, that's as far as I've gotten already. So let's try the next pin. Pin 6 looks like it should be 90 volts. So we'll go to pin 6. Let me put this back on RF. Pin 6. What? Wait a minute. 1, 2, 3, 4, 5, 6, and 7 pins. This is pin 6. Oh, you know, there's a capacitor to ground right on that pin. 0. What is pin 6? What is pin 6? What is pin 6 on V2? 6 on V2. Well, let's look on the schematic here. I think I might have it. Get it here. Gonna get the schematic up here. Pin 6 on V2. Where's V2? V1, V2. Pin 6. Yeah. Wow. Okay, so there's no screen going on here. There's no screen voltage. This capacitor may be shorted right to ground. That means the other side of the 150K resistor I should find a high voltage. This could be open also. So I'll go on the other side of this 150 and we'll make a measurement there. Other side of the 150. Okay, so is it really a 150? Brown, green, yellow, 150. So once again, this is the pin 6 should have 90, showing nothing. Other side of that resistor, 260. Now, how hot is that resistor? 260 volts across it. It's possible that the capacitor has failed and the resistor burned open. It looks fine though. Well, I didn't, you know, basically it's pretty much the first tube and the third terminal I tested, and bingo, I got something quite serious going on here. Let's just try a different scale here, just because. That's the kind of guy I am. A little tiny bit there. And this should put it over. Yeah. Okay, well, we can't really go further without dealing with this problem. It's serious enough that it has to be resolved straight away. That was a combination of the speaker rattling and then my stomach growling. In case you heard those things, you wonder, what are those weird sounds? Let's try, first we'll check for residual voltage here. Around the components we've been checking. I'm on the 2-volt scale, so let's give it a chance. That's going up. And the other side of the, so this is one side of the resistor, 3, 6, other side, 0 still. Let's, I guess, make a resistance measurement right on that resistor. Supposed to be some hundreds of thousands of ohms. Looks like it's a little more than that. Well, that resistor's open. That's what that's telling me. Let me just swing this around so you can kind of see better what I'm up to. So the resistor's right here. Still hard to see it in that camera, I know. A resistor. Now, what about that capacitor being shorted, which is probably the real problem. So I'll put this on the ground. And if I touch the terminal that the capacitor's hooked up to, oh, it says open. So that's telling me the capacitor is not shorted. That's right. This is the ground. It's connected. It's connected. Well, I can test it this way. Yeah. So the good news is the capacitor is fine. The resistor has just left the planet. It needs to be replaced. So that's step one. I gotta do it. I have to fix this on right now. I can't carry on without fixing it. So we'll chop out this resistor. So the effect of not having a screen voltage on the tube means the plate can see the grid, and you end up with undesirable interelectrode capacitance. So what's happening on the plate, which is powerful, can, through capacitive effect, influence the grid. And so you get a feedback thing happening there. Shoot them out. Test them again. Test the meter. Test the resistor. Here's one open puppy for sure. Yeah, completely open. Brown, green, yellow. So that's 150 K. 150 K. So that's with a yellow. So these are all my 15s. And all I got to do is look for one with a yellow third band. And if I find one, that's what I'm after. I think that might be one. There's another one, a style of resistor I don't like very much. Looking for a little bit of a higher wattage one, but I don't think I have a higher wattage one. Because having had this one burn up, it might be suggesting it's a little low in terms of its watt rating. So I think this is a much higher wattage resistor. Okay, let's check the two resistors and see if, and also I'm just gonna, let's just look in here. Where are we on this? Where is this? This resistor is coming off of V2. This one here, 150K. Yeah, just making absolutely sure I'm on the right, in the right direction. 150K. You should see that nicely on here. Ooh, 15K. $150K. Well, what I thought was yellow must be orange. That's why I like to test these first. So we're going to try it with this guy. If I get them in, if I'm gentle with this resistor, it'll be fine. What you can't do with this style of resistor is bend the leads a lot. Or the end caps come right off. We don't want that to happen. Okay. Set is definitely off. Lead. to put this in now where I have to bend it much after it goes in. I got my hand right in this thing. Hope there's nothing charged up in it. That's ready for soldering there. So if I'm working with these kind of troublesome resistors, if the cap comes right off, that's great. I know it's wrecked. I can just grab another one. But if the cap doesn't come off, but in fact I've loosened it somehow, so the internal contact is poor, I can't see that. It's not obvious. So I suppose I better measure the resistance of this once I get it in. Okay, now let me just hold the wire here. How much difference would this make to this set? Well, I don't know. I imagine it's going to make some kind of significant difference. And could this be why we didn't pick up any stations with it? I suppose it's possible. There we go. Thumbs up. She's all fixed now. Check the resistance. I think there's many times when I say I'm going to do something and then I don't actually do it. I think that happens a lot. Yeah, good ideas not implemented. 150 ohms. 150K. There she is. 150K. Success. Okay, yeah. Now, I wonder if we can notice any difference in its operation already. You know, that could be it. That could be the thing. Okay, dim bulbs for sure. John, dim bulbs behave normal. Bench here a little bit. There. Here. Okay, what do we got happening now? We're in RF mode. We're still on dim bulb here. Seems a little different. I hear a metallic echo. It's got to be that feedback thing. Sounds a lot better to me already. We're on B680 here. Let's stick it on that outdoor antenna, which is not connected to anything. Let's stick this on. I can go get my loop antenna again. Well, let's just give it a long clip lead right now. I think it's behaving very, very differently. That's what I think. We'll put this nice antenna right over here. Carefully positioned antenna. So that chucky noise, that's interference I hear all the time in my shop. That music did not come out of this. I'm going to go get that antenna. I'm going to get that antenna. Okay, this is a loop antenna lead. I think this thing's behavior is really very different. That on there. And we'll clip the probe on here. Turn down the volume. Turn up the volume. Let me tune the antenna. I haven't even tuned the antenna. So turn this down. The antenna may be tuned to 640. I think that's the station I left it tuned on. Turn it up a little bit. 590. Sports station from Toronto. Its nickname is the Fan 590. Somebody peeking around the corner down there. Oh, here he comes. Oh, he's looking for the visitor cat. That's what he's doing. Okay, first direction. Tuning. Direction. These antennas have a really sharp and deep null, and this is really the power of the antenna, is the null. It's not the reception. It's the rejection.
State Farm Canada is now Desjardins Insurance. Learn more at desjardinagents.com. So this is your very first day on a 1-800-GOT-JUNK truck team. I'm really excited. Of course you are. This is a great job. So tell me.
640.
What do we tell people?
Tune the antenna.
Baseball diamonds in the summertime, but in the wintertime we had our hockey rink, and we could play ringette there, and then we also had just like our fun rink for people.
Both these stations are coming from Toronto. I believe the transmitting antennas are somewhere around Toronto, roughly the same direction. I'll turn the antenna. I'll rotate it 90 degrees. Same thing. Great. 680. Not very sharp. Well, you know what? I think I'm going to stop here and spend the day reveling in my success here of having found a open resistor very quickly and having dramatically altered the operation of this device already. So I think the story here is I purchased this off the internet. When it arrived, I believe it was in better working condition. And over the time I've used it, the dozen or 20 times I've turned it on, or 30 times I've turned it on and used it, somewhere along the line that resistor gave up the ghost, and it went from working well to not. Now maybe not, maybe it's never worked well, and that's why I've never had really great luck with this thing. Fantastic, yeah. Just leave it like that and go and enjoy my day doing all kinds of other stuff. Thanks so much for watching, and next video we'll just carry on with the testing and repairs to this guy. Fantastic.